Hi, everyone. This is Michael Lee, founder of the Data Incubator. We're a data science training and placement company. So before we get started with today's episode of Data Science in 30 Minutes, I'd like to take a few minutes and just say a little bit about our program. So as most of you probably know, we have a fellowship for PhDs and master's students who are looking to enter industry as data scientists. And it's completely free for the fellows who get in, so you can apply online at www.thedataincubator.com. We also offer online courses for people who are currently working professionals, as well as corporate training options. And if you're interested in either of those, you can also go online to www.thedataincubator.com to learn more. So today we're going to be doing another installment of our series, Data Science in 30 Minutes. So this is a regular monthly web series, and it's really about data and its role in the world. Past speakers have included Kirk Bourne, who is the Director of Data Science at Booz Allen Hamilton, Becky Tucker, data scientist from Netflix, Holden Corral, an engineering lead from IBM and one of the core contributors to Apache Spark, Zubin Garmani, the chief scientist at Uber, Sam Swift, VP of Data Scientist at Betterment, and a TDI fellow, or former TDI fellow. So if you're interested in learning more about them, you should go to our website and you'll be able to see all of those past DS30 videos. And before I introduce today's speaker, I want to remind everyone that you can pose questions in the YouTube chat area. You have to be logged into YouTube, but this is the area once you're logged in on the right-hand side of the screen. We'll monitor that, and we'll pose those questions to the speaker towards the end. But feel free to start putting questions in now, because we'll keep track of all those questions and ask them at the end. So without further ado, I'd like to introduce today's speaker. I have this pleasure of introducing a kind of a real leader in the data science community, Shioulin Sam. She's a research engineer at Cloudera Fast Forward Labs. And she has a very, very diverse kind of an interesting background. And maybe after her presentation, we'll ask her a little bit about that. But in her previous life, she was an angel investor focusing on women-led startups. And she's also worked as an investment manager, designing quantitative trading strategies. So she holds a PhD in electrical engineering and computer science from MIT. So without further ado, Shioulin, would you like to kick it off?
Sure. Thank you, Michael, for the nice introduction. I'm very happy to be here. Thank you for inviting me. I have a set of slides that I was going to share, and then I also wanted to share some of the prototypes that we have built internally. So let's do that.
All right.
Okay. Right. Let me share my screen. That's the first step. Okay, can everyone see this?
Yep.
Okay. So today I thought it would be interesting to talk about machine learning trends, especially from the perspective of what I do at work. At Cloudera Fast Forward Labs, I focus on two things. First is the research, and second is client advising. And it's through these two lenses that I hope to share with you what my thoughts are on where machine learning is going. At Cloudera Fast Forward Labs, we see ourselves as the bridge between academia and industry. And our mission really is to fast-track knowledge transfer from the lab to the industry. We bring technical innovations to industry applications. And we do that in three ways. First, we have the strategy engagement, where we help clients develop and execute data strategy. Second, we have the prototype development, where what we're essentially doing is to turn science experiments into actual products. And lastly, we have the advising and research subscription, and we use this to help us and help our clients stay on top of emerging technology. As part of this research subscription, we publish reports about every quarterly, and the goal of the report is to highlight an emerging capability within machine learning that we believe will become important for the business community within the next 6 months to 2 years from when the reports are published. These are a set of reports that we have done so far. We are on number 10, and that's the one that I'm leading, and we are supposed to launch that sometime end of March. So there are so many topics. How do we choose? Well, we choose topics using 3 criteria. The first one is that topics have to be interesting and useful. Second, we have to be able to build a prototype. And third, the topics have to be timely. Purely algorithmic research that comes out of academia is not super duper interesting to the business community unless we can frame it as a capability. And having the prototype requirement is a way for us to filter internally for these types of ideas. We need to be able to take the algorithms and translate it into a capability. So we have to be able to build something that depends on these breakthrough algorithms. Otherwise, it's not really useful in our minds. Lastly, these breakthroughs have to be timely, meaning that it has to be more possible now than it was 1 to 2 years ago. And it has to be even more possible 1 to 2 years from now. All these reports cover a couple of things. First, we go through a general introduction and gentle introduction of the capability, and then we dive into the technical nitty-gritties. After that, we talk about the prototype, what we did, what we tried, what worked, and what didn't work. For clients who are interested in building this capability or implementing this capability, we dedicate a chapter on landscape that will hopefully help the source or build decision. Finally, because machine learning capability is so transformative and it has unexpected results, we dedicate a chapter on landscape. We close these reports with a really fun short sci-fi story, and the goal really is to try to get our clients to imagine in a very unconstrained way what this capability can do for their business. So today I will focus on 2 of our reports. The first one is on semantic recommendations, and the second one is on multitask learning. I wanted to start with the prototypes that we build. So give me a second as I switch over. Okay. Can everyone see this?
Yep.
Okay. So this is the Deep Bargain Bookshop. This is the prototype that we built for our recommendations report. This bookshop has the best prices on a very limited selection of books. Our recommendation, which is built on the latest and greatest in machine learning techniques, can recommend books from our selection based on any book that you enjoy, including books not in our system. Some of you will recognize that this is possible because we don't have a cold start problem in the system. Let me orient you a little bit. When you first land on this page, there's a left panel. And if you don't have any particular book that you like, you can scroll through our recommendations based on the current New York Times bestseller. So this particular book is a current bestseller, and it's a Beastie Boys book. If you find this interesting, these are a set of books that we recommend based on your interest. If you keep scrolling, you'll find more other books that's on New York Times bestseller. For example, this one by Bill O'Reilly. If you're interested in this, here are a set of books that we recommend. You can just keep going.
And then while I have you here, you said that this problem is a little easier because you do not have a cold start problem. So for those in the audience who don't know about what the cold start problem is, could you explain that and how it applies to this project?
Sure. So this capability where we can recommend books based on any book that you enjoy, not just including books that our system can see, is only possible because there's no cold start problem in our system. The cold start problem happens, and I will talk a little bit in the slides that follow, but essentially cold start problems make a recommendation system only able to recommend items that it has seen before. It doesn't really know what to do with new items. And in the slides, I will kind of try to go into the reason behind that.
Cool.
Okay, so and let's go back to the right panel. So this is a set of books that we recommend if you like Beastie Boys book. And here on the right-hand side is a little more description and detail about this particular book. So you can see, okay, Being Jordan is recommended, and here's a description about Being Jordan, and here's a description of Scent of Rain, and so forth. This little blob here is actually a visualization tool. And this is the tool that allows us to understand why the system is recommending certain things. You will see that the Beastie Boys book is right here. And the books that we are recommending are actually just right around it. And This, keep in mind, is in a two-dimensional format, so there's a lot of information that's lost. But it does a pretty good job explaining why we pick certain books over the others. Each dot in here are books that we have in our system, and different colors represent different categories or genres. And I will show in a second, you can actually use this to navigate through our entire catalog, and it's a different way to interact with these systems. So in this little text box here, if you have a particular book in mind that you would like to get recommendations for, you can type it in. I'm going to use Harry Potter. Click Submit, pull up a bunch of titles, and I'm going to click this one. Okay, so this brings us to the Harry Potter book and recommendations based on that book. And here is the visualization. Make it bigger. Harry Potter is the target book, and it is something that the system hasn't seen before, but it can recommend books that's within the inventory because there's no cold start problem, and really because the system understands content that's in these books. You can see that all these books are being recommended because they're right close by this particular target book. You can also kind of scroll through and look at different titles here. If you see any books that's interesting, you can click on it. I'm just going to randomly pick this. If you like this religious book, there are a bunch of other books that we recommend based on your preference. You can go to other spaces, go a little further away, and then go here, perhaps, and we recommend another set of books for you. So that is our recommendation system prototype. Now I'm going to switch gears and show you a different prototype. This prototype is called Newsy. This is a prototype that we built to illustrate the multitask learning capability. And what it does is it allows articles to be analyzed under two lenses. The two lenses essentially are the two tasks. So we can either analyze articles as a broadsheet or analyze them as a tabloid. And they're very different, starting from the way things are arranged in the front page and actual paper. Here are some articles on New York Times and on New York Post. And in this particular article, these are recent articles that's pulled by our API. So this New York Post article, Reputed Mobsters as Feds Gave Detector Cheat Sheet for Trial. It's classified under the tabloid lens as a New York City regional article. And it's classified as only 50% news if it's a broadsheet article. The next one, Broken Glass Rains Down on Sidewalk in Midtown. Tabloid once again classifies that as 99% New York region news, and the broadsheet classifies as 99% news. This one, Shut Down Pain, gets classified both as news and under both lenses. You can click this article, and when we click it, this system behind the scenes is essentially analyzing the article as it reads it. And first, it starts by thinking it is a business article, and then it thinks that it's some kind of entertainment article, and then it thinks it's a news article. And then at the end of the article, it has made up its mind and it thinks that it is actually a news article. So this is the prototype that we built. I'm going to go back to the slides and kind of try to give an idea of how we built it and why it works. Okay, can everyone see this?
Yep.
Okay. So the first one I'll talk about is on semantic recommendations. So the recommendation problem is mostly associated with e-commerce systems, but the application is actually quite broad. Anytime you have two types of things that need to be paired together, moviegoers and movies, sales representative and customers, you essentially have a recommendations problem. The task is, given how these interactions have gone in the past, to predict a new set of pairings that will work in the future. And In classical recommendation systems, what we do is very simple. We start by looking at the user, and then we look at these items that this particular user has liked. And then we look for similar users, and then we recommend items that these similar users have liked to you. So this sometimes works, but what the system ended up doing is really not understanding content. It's just recommending based on similarity, based on patterns of what you like and what you don't like. And all it's using in terms of the information coming in is a set of user item interaction. So it has removed everything that's valid about the world and just represents the user and the item and their way they've interacted in the past. Now, this type of recommendation system requires that user interaction matrix, which is easy to build, but does not give you much information. And in a way, you can think of this representation as a very shallow representation. Matrix factorization tries to do better. It tries to enrich the user item representation. So instead of representing things to you because others similar to you have liked it, we look at the factors. We try to build a set of factors that will capture all the information within the user interaction matrix, and then we base our recommendations on these factors. So instead of recommending a book to you because somebody else has liked it, I'm recommending the book because you like the genre sci-fi, for example. So this makes it slightly better. But both of these systems suffer from what is known as the cold start problem, because these systems don't know what to do with new items. In the collaborative filtering approach, for example, we only recommend things to you if others similar to you has looked at the item and decided that they like it. But if nobody has used or looked at the item, then there's no way to recommend anything to you. One approach to fix this is to build something that truly understands content. Now, to do that properly, we have to be able to build a system that can represent content properly. If you do it naively, let's take a look at this example. What you end up having is, for example, 3 books. The first, High Hopes, The Rise and Decline of Buffalo. The second, The Buffalo Book, The Full Saga of the American Animal. The third book, Of Bison and Man. If you use a naive approach, your system will find that the first book and the second books are related because of the word buffalo that appears in both. But it will actually fail to capture the real relationship, which is between the second and the third book, because it just doesn't understand that buffalo and bison have the same meaning. Emerging technique from deep learning has actually allowed us to represent content better. And one example is embeddings. Embeddings are really just a learned representation of words. So you translate some words through some kind of supervised machine learning training algorithm into some numbers. And when you're done training, what you have is concepts that are considered similar are grouped together. So these are countries, these are states. And then the way that they group together and the position on these 2D matrix, for example, allows you to do really fun arithmetic. So this one, for example, Washington, D.C. minus USA plus France will give you Paris. So with embeddings, we're able to capture rich semantic information within the words. In recommendation systems, we need to embed both items and users on the same space. In the previous slide, we are only embedding words. So this is known as multi-modal embedding. And essentially what we're trying to do is, for each item, represent item as the text. So we're actually using the content. And for each user, we recommend the user as a series of texts that this person has liked. And then we formulate a supervised machine learning problem to find a bunch of vectors that represent the user and the item. And when we make recommendations, we just locate a point and recommend things around it. The use cases are pretty straightforward. So we can use this for new product recommendations. Notice the word new, and that's only possible because there's no cold start problem and because our system truly understands content. We can also use these systems to recommend financial products, and we can use it to compare customer and customer service representatives. So I'm going to shift gears and talk about multitask learning.
Quickly, just before we do that, so if we sort of go back to some of the slides you were showing earlier,
Sure.
and this is maybe a question that's more for the advanced listeners. It sounds like you're using techniques like word-to-vec or similar word embeddings, or using sort of more contextual word vectors like Elmo.
We're not using word-to-vec per se. We're using the concept of word-to-vec to help us translate this particular problem into a supervised learning problem. I can show you details with another slide on how this is done. Would you find that interesting?
Yeah. I mean, if it's not too,
okay,
if it's not too hard to find or get that up, don't want to derail your presentation here.
Okay, let me dig it up. I'm going to stop sharing for a second.
All right.
Okay. 1 second. Okay. Okay, here. Okay, can you see the screen?
Yep.
Okay. So the question is, how do you build embeddings for a recommendation system? Because it's multimodal. In word2vec, you train the model on a large corpus of words, and you make it predict the word before and after. And that's your essentially supervision, right? In this multimodal embedding, we have to find a way to represent users and items in the same space. So the way we do it is as follows. We have users, and we represent them as a series of items, which is the text of the description of the book that they read, or the review of the book that they've read. And then we have the stars that they assign to this particular book. So what we do is as follows. We first randomly take out one item. In this example, we took up item 5. We set that aside. And then we randomly take up 3 remaining items, and we put it here. And we use this to represent the user. And then we link the user and item using the rating of this item. So item 5 has 1 star, and then we use that as an output. And we do this many, many times for each user history. Essentially, it's data permutation. Allows us to get many, many samples. And we also have a negative sampling data point. So item 20 has never been seen by the user. We take 5, 1, and 3, which has been seen by the user, and assign that 0 stars. So that's essentially how we do it. Does that help?
Yeah, no, that's really interesting. So in some sense, you're both sort of artificially hiding the data from yourself and kind of trying to predict the data that you've hidden, as well as sort of the assumption that if the user hasn't read this book, they're likely not to have liked it. So let's pretend that they would have given them a bad rating.
Yes. And we need this because you kind of need ratings of all classes to train the system.
Okay, and you do this across all users as well?
Yes.
And presumably the training is across a sort of a deep neural net or some sort of neural net?
Yes, it's a deep neural net. I think it's an LSTM, but if I remember correctly, it is a neural net, yes.
And then so the vectors you get out are some sort of intermediate step in that neural net.
Yes, so when we train for the output to match. But what we really want is the embeddings before the output layer. And that tells us, what user is being represented and how books are being represented. And in this system, we use a vector size of 256.
Cool. And then, sorry, back to your other slide here. I think you said for the potential applications, one of them was financial services, or recommending financial products. And what was the other one?
You can pair customer with customer service reps. So this is a separate way of a different way of using the recommendation system. It's not something that's generally used, but like I said in the first slide, these systems are actually very general because what you're looking to pair is any 2 types of things, and you just need a way to rank them and pair them.
Got it. So for financial products, you're kind of looking at the fact that the financial product probably needs to have some textual description.
Yeah.
You look at user ratings for user reviews for those financial products, let's say.
Yes, exactly.
But it could very well have been like Amazon reviews of I don't know, toilet cleaners or whatever.
Yes, it's the same.
Got it. Got it.
And then, even if it's financial products or toilet bowls, they are what we're working off is the same.
Got it. And then for customer service reps, you're kind of looking at that text. Is the text or the communication between the customer and the service rep?
Yeah, we're looking at text. We're looking at, you can look at feedback.
And yeah, feedback.
Yeah.
To get your
Yeah.
Very
so
cool.
what we really need is the feedback, because without feedback, you cannot turn it into any supervised learning problem.
Oh, interesting. So I guess, yeah, this is perhaps where you add in a bit more information than is in Word2Vec, because Word2Vec is just sort of like, here's a general embedding for English, full stop.
Yep.
Whereas you're saying like, here's an embedding that is useful for rating book ratings and the exercise of rating, you know, or the exercise of like deciding if a user is going to like a book.
That's correct.
Specifically geared to that, as opposed to just like generally, here's an embedding, a vector embedding or word embedding that's useful for English.
That's
and you
correct.
Figure out the rest of it.
That's correct.
Cool. Cool. Yeah. Sorry.
That's okay.
That's very interesting. Keep on going.
Okay, so I'm going to spend a couple of slides on multitask learning. You've already seen the prototype, but what essentially multitask learning allows you to do is to train machines that can master more than one task. Excuse me. So this is kind of a more realistic problem, because as humans, we don't really just know how to do one task. We can do multiple tasks. And machine learning today, and many times, we're actually forced to formulate the problem as a single task problem, but we can actually build models that can predict multiple tasks. Here's a single task machine learning training procedure. You start with the label, you start with a set of data, and then you ask the model to predict the label given the set of data. In multitask learning, you provide two sets of labels. So the first label is the risk of patient being exposed to pneumonia. The second label is the number of white blood cell counts that is in the patient's body. And you ask the model to at once predict both the label of risk and the label of white blood cell counts. And when it's trained properly, you can just feed it in some symptoms, and it will be able to spit out two predictions. The major difference between single task and multitask functions are that the way that we define loss for single task function is different from the way that we define loss for multiple task models. In the single task functions, this is the general approach that we use. We run the model, we look at the prediction, and then we measure the difference between the predicted and the actual, and we call that our loss. With multitask loss function, because we have now multiple labels, label 1 and label 2, and each of them have a loss associated with it, we need to combine these into one single number that the model can optimize on. Multitask approaches apply to almost any machine learning methods, for example, decision trees. But what makes it more interesting is multitask neural networks. So the way you turn regular neural networks into multitask is similar to what you would do in other simpler modeling approaches. You first change the output node from one output to multiple output nodes, and then you have to create a composite loss function, and then you can play with different architectures. Here is a simple one. The input data comes here and goes through multiple shared layer. Task 1 is here and task 2 labels here. And both of these task 1 and task 2 nodes have access to the same information and the same representation in the shared layer. You can think of these two layers as really just a linear combination. So it picks certain features from the shared layer, and it uses that to predict task 1. And this one picks certain features from the same shared layer and uses that to predict task 2. This is suitable for related tasks, but it may not work for tasks that are not super related. A different architecture looks like this, where we actually separate out the representation for shared and the specific. So input data still goes into the shared layer, and the shared layer is connected to both task 1 and task 2. But we add in a task-specific layer that only connects the shared layer through the task-specific layer to the task-specific output. We do the same for task 2. So using the neural network this way allows us to get task-agnostic and task-specific representations. And we can get gains for loosely related complex tasks. How are multitask learning being used today? They're being used in drug discovery. The ability of compounds to bind to several different kinds of receptor sites can now be predicted concurrently. It not only allows you to predict it concurrently, it often results in a model that's more representative and more generalizable. In healthcare, models trained by multitask learning outperformed, although not all, single task learning models. So for example, predicting hospital stay length, mortality rate, and so forth. If you think back about the example that we used in the beginning, when we're trying to predict the risk of a patient of being high or low when they're being exposed to pneumonia, using that alone is a very coarse description. And what we ended up doing is to add in the white blood cell counts. So when you add in something that's more granular, you actually end up with better models. Essentially using more information to help you build a model. The information is there already, why not use it?
So I think what you're saying is that this task is, multitask learning is useful because obviously, right, or the benchmark that you have to prove yourself against is, well, why not just have a bunch of single task learning?
Yes.
And I think what you're saying is that those labels for the other tasks actually contribute information that's useful for my current task.
Exactly.
And that there's some magic that's happening there. I guess through the magic of deep learning, where that information gets propagated to the output.
Exactly. So I think what's happening at heart is when we train neural networks using multitask, we end up with a representation that is more general, that can extend to cases where it allows you to predict other things, because you're essentially forcing the model to do multiple things at once. So you're kind of pulling in attention from somewhere else and putting it to work at another task.
Got it.
Okay, here is just a little bit about the prototype. This is the first edition of New York Daily News. This is the first edition of New York Times, and just by glancing at it, you know how these are very different. So then our prototype essentially allows us to look at these two things via the two very different lenses. So that's all I have for today.
Cool, cool. So yeah, so I think obviously this has drummed up a lot of questions, and. So I'm just going to start throwing some of them at you that I think are really interesting. So when you compare some of your text analysis or NLP techniques using some sort of deep learning or neural net, and you compare that to something like a latent Dirichlet layout allocation, right? I'm curious, how does that compare? Maybe just to make this simpler, one axis of comparison can be just pure performance based on some metric, right? And the other one that I'd be interested in is the interpretability of the factors, the underlying factors that you find, or the hidden factors.
So let me repeat the question. The question is, when we compare approaches that we use, by building an embedding, and we compare it to like topic modeling, is that what it was?
Yeah, latent Dirichlet allocation, but I guess any sort of standard topic, pre-neural network topic modeling.
Right.
Algorithm.
So topic modeling is a type of unsupervised learning model, and you don't really need to provide labels, right? What you need is just dump a large corpus of text at it and ask it to generate a couple of types of topics. Then each topic is represented by a bunch of words. So that's topic modeling. You can potentially use topic modeling in, so it's a way to vectorize text, but it is a superficial way. You can use topic modeling to analyze, these, for example, these book reviews, and see what kind of topics come up. And then you can build a matrix that links a user to the features that you find through topic modeling. And then you go ahead and use recommendation system that's based on features, so some kind of matrix factorization approach. But you are really just explicitly telling it to matrix factorize using topic modeling. The approach that we end up using, which is the embedding approach, goes a lot deeper in terms of finding representation. It is expressing each user or each article in a 256 size vector versus expressing just a bunch of articles into a series of topics. So it's a very deep representation. It captures semantic information, it captures relatedness, and it captures all these cool things that embeddings allow you to capture.
Okay, cool. And then one of our users said, was asking about, when you show that example of that Beastie Boys book, it looked like the books around it weren't necessarily related to other bands, right? Like I would maybe expect the NSYNC book. I have no idea if that exists. But, like the Britney Spears book, I don't know if that exists either. But like things like that. So I'm kind of curious about, or they're kind of curious about, well, how do you measure success with these recommendation engines?
Yes, that's a good question. Recommendation systems are hard to measure because you ultimately need to do some kind of A/B test if you want to know if it really works. But in our system, the way we've built it is that we used the book reviews that a user has generated for each book. So that is one disconnect there. We don't use the summary for that book. We use the reviews. So then you can see how sometimes that could get you different, you could be extracting different contents. And the reason we do that is because that data is available and we don't have a good way of representing each book by a really nice summary.
So a lot of you don't have a great notion of like, what's the canonical summary of this book? Is it the New York Times summary? Is it the New York Daily Post summary or whatever?
Yes. So for the semantic recommendation system specifically, we use the Amazon book data set. And that essentially is a user and a bunch of books that they've rated along with the reviews of the book. So it's a proxy for the content of the book, but it doesn't fully represent the book. And sometimes the quirks that you see in the system is from this. Can
you give an example? I don't know if you've discovered an example of a quirk, a quirky feature that you can share.
I actually don't have one off the top of my head, but I've heard from various people who have played with this prototype that sometimes it kind of makes sense, but sometimes it doesn't make sense. And there's a couple of reasons. First is the data issue, and second, the data is also very dirty. We don't have a lot of feedback or good ratings. Most of the ratings are provided by a minority of users, so that kind of skews the system.
Yes.
So that's a very common problem that happens to all kinds of recommendation systems.
Yeah, no, look, it's very true, right? Like if you look at the rule of Twitter, it's something like 5% of users contribute like 90% of the content. So if you analyze the text, it's not necessarily representative. And then, so with Netflix, right? If you think about how the Netflix challenge measured success, they just looked at like, look, there's a holdout set, and I'm going to sort of see like, can you predict the answers in the holdout set? I guess you're implicitly doing that because of the way you're setting up the training, right?
Yes, we're using that to judge our models, but it doesn't come up in our prototype. Because what we're really showing is a set of recommendations, and then you can kind of scroll through it and decide if you think it's correct or not correct. One of the cool things that our prototype allows you to do is really interact with these systems differently. You can scroll through our catalog. You're going to go to different spaces, and you can pick on any dot, and it will bring up a set of recommendations. So it is a way to explore, and it's also a way to find recommendations.
Got it. And then if you were to look at, so just to make sure I understand the architecture here, it's not that every item in your recommendation engine has some canonical text. It's really every user item pair has some canonical text about that relationship between the user and the item.
Yes, yes, exactly.
And that's okay. And is that I guess broadly true of that? The algorithm you developed is that the text resides in the user item pair, not the item.
The text is about the item, but it's provided by the user.
Okay. And does it
So the
change
data
if you does it change if the text is not provided by a user, but you have a canonical item?
No, we've kind of filtered the data because it was a very dirty data set. So we kind of filtered it to get data that's as clean as possible. So each user has a sequence of interactions with a set of books, and they rate these books, and then they also provide feedback, review on these books. And that is the data set that we start with. So for users who only rate one book, we don't use that user. For users who rate like 200 books, 500,000 books, we also don't use that user.
Oh, because you think that there's probably something a little suspicious about their ratings?
Yeah, because it doesn't really give much information, right? You rate every book, and it's just at the extreme of what the average user rated books should be.
Got it. And then some people were interested in the reports. Are they available for free, or do you have to be a subscriber?
Yeah, so unfortunately, the reports are only available through our research and subscription program. As part of this program, you get access to all the reports that we publish. You get to play with all the prototypes. And you also get 4 hours of monthly advising time. And our clients use it essentially to talk through the report to see how they can use it within their enterprise, and as a way to generate ideas and essentially help them level up data science.
Got it. And then kind of the general question, obviously, you've had a lot of experience working both as a data scientist and kind of as a quant on Wall Street. What's your advice to people who want to get started in this kind of quantitative data field? There's so many tools out there. What should they learn? What skills should they prioritize?
I think that's a hard question. So how do you start in this data science field? Is that how I should think about this? Okay.
Exactly.
I think it's always important to kind of play with it yourself first, because then you will know if you like it or not. That's very important, right? I always think going into a field just because it's hot is not the right reason. You have to love it. And the way to find it is find and confirm that is really to try a bunch of projects. Try the Kaggle data sets, or try whatever that you can find your hands on. For example, if you think recommendation systems are cool, try to build a recommendation system yourself. And then you will see what are the problems that come with it and what you have to focus on. The other is, if you have friends who are in the industry, you can always ask them to point you to interesting problems. If they can share data, that's even better. If they can't share data, at least you know where to look and how to look. But it's always important when you build these, when you engage on your data science journey, to start with something simple, because it's easy to say, oh, I want to do neural networks. And then I can code in PyTorch, and I can code all these crazy fancy neural nets. But that also means that sometimes you fail to see the big picture. What is data science good for? How is it being used in an enterprise? And how do you actually connect data science to a business problem? So those are the things that I would think about.
Yeah. No, I think look, I think you're absolutely right. There's obviously a lot of excitement and interest in data science, and a lot of the excitement is at the things that are at the very cutting edge, right? Your deep neural nets, your LSTM. People love that kind of stuff, and that's great, and I'm glad it's getting a lot of people interested. But just to sort of echo your point, data science is not a spectator sport, right? You have to really do it before you can actually claim you're a data scientist. And that takes a lot of work.
You have to do it. You have to get your hands dirty. You have to understand what dirty data and bad data means. And then you will kind of appreciate, how much work it takes to get something into a form that you can actually use.
Yeah, got you. So and that's what we encourage at the fellowship here at the Data Incubator, and for our online courses, and for all of our corporate training, is getting people to get their hands dirty, we have a Jupyter notebook system that we put up in the cloud where you can start working on the code right away and start playing and tinkering with real data. And I think that makes a huge difference, right? Just getting your hands dirty.
Yeah, one thing I do want to add is there's a lot of focus on trying to get results fast. It is good and it is bad, because when you do it too fast, you actually don't know what's going on under the hood. So I always think it's important to look under the model and understand the basic of what's going on first. And then you can abstract to a higher level and go from there. But if you just start at the high level, you will always just stay there and you don't really know why things don't work, and you can't figure out why things don't work.
Got it. Yeah, I totally agree. So anyways, I'd love to thank Shioulin for joining us, and thank you to the audience for attending and listening. I hope you've enjoyed this. If you're interested in learning or hearing more of these data science in 30 minutes, go to our website, www.thedataincubator.com. And you'll find links to both this Data Science in 30-minute episode as well as the previous ones in the series. And of course, if you're interested in our free data science fellowship for PhDs and master students, or our online courses for working professionals or corporate training, you can also go to our website and check those out. So thanks so much.
Thank you, everyone.